Okay, enough of theoretical equations. Now let's actually apply those equations to a unimolecular diffusion case. In this one, oxygen, which will be A, is diffusing. So technically this is the one that actually moves through carbon dioxide B, which is under steady state conditions, with the carbon dioxide non-diffusing. So that is literally the instruction in which we have been working with. A is diffusing through B, which is not diffusing. The conditions are as follows. Pressure is 10 to the 5 pascals, temperature is 0 Celsius or 273 Kelvin. The length is given, so remember that delta is the difference between C values, or in this case the length. It's equal to 2 millimeters, which is 2 times 10 to the minus 3 meters. We are also given the partial pressure of oxygen, I'm going to guess, so this is oxygen, 1.3 times 10 to the 4, and the second value is 0.65 times 10 to the 4th pascals. So as you can imagine, the further away, the less oxygen we have, which makes a lot of sense because diffusion is stronger near the initial point and it declines as it goes to the final point. Diffusivity of oxygen in carbon dioxide is given as 1.87 times 10 to the minus 5 meters square seconds. This is a quick diagram. This is, let's say, oxygen goes through the path and diffuses in CO2. Now the main question, remember that always go to the actual question and know, because don't get distracted if you see unimolecular diffusion. Just go directly to the question. Calculate the molar flux of O2 in the mixture and molar flux of A. Remember that now we cannot just simply assume this is JA. Actually, we will need to solve the whole equation. Well, actually, no, we don't need to solve it because we already work with them. And because we are given pressures, I think it will be convenient to work with partial pressures. You can either go for this one or this one. I don't like this one because we need to calculate concentration, which is not that huge of a deal. But if we have an equation which already accounts for only pressures, we should use it. And here it is. Here we go. The pressure is given. Pressure is 10 to the 5. So here we go, 10 to the 5. Diffusivity is given in our convenient units. That's great. The R is a constant which can be found anywhere. Temperature is given 273 Kelvin. The length, or the difference in the path distance, is 2 times 10 to the minus 3. And this is very interesting right here. Maybe you think I got something wrong, but no, 10 times 10 to the 4 is actually this value, 1 times 10 to the 5th. Why did I do this? Just to compare directly these two numbers. If they are on the same basis, 10 to the 4th, I can compare directly. And as you can see here, in both cases, we have positive, positive. And not only that, this will be greater than this one. So expect a natural logarithm value positive and greater than 1. All these numbers give me this value, and the natural logarithm give me this value here. Calculating the total, 0.02967 moles of oxygen per square meter per second. If we had, let's assume we have one square or one circle of an area of 1 meter square. This means that we have, let's say, 100 seconds. So this time 100. We have 2.9 moles passing of oxygen through this area of 1 meter in 100 seconds. So that's just to give you an idea. For me, it's very important that you try to actually feel a grasp or understand with numbers that you actually can understand. I think 1 meter to second power is very, well, straightforward. 100 seconds is almost 2 minutes. 2.9 moles, you can count them. They are almost 3 moles. So that's how fast this experiment is happening. Okay, this is the same. We just change this to scientific notation. And now let's continue with B. Calculate the total moles in diffusion per unit area in 5 seconds. Now the interesting part I wanted to show you, I was telling you that time should not be of concern to you guys. And especially this is steady state, so technically I'm going to assume the quasi-steady state, because I know with time, if this material is diffusing, it will eventually run out. I cannot assume that as time passes by, nothing happens. I know that as time passes by, oxygen will diffuse completely. But for now, I'm just going to assume that the diffusion is constant, or the moles in diffusion is constant, at time equals 0, time equals 1, all the way to time equals 5 seconds. And if I were to do an average, well, of course, since it is the same value, I just need to plug in the value right here and the change in time, which is 5 seconds. As stated, this is what I was telling you here. I use 100 seconds. This is now 5 seconds. And this will be the value, 0.14 moles of oxygen per square meter. And now getting more technical, if the spill is 0.45 square meters, calculate the molar flow. So as stated before, the flow can be calculated if we get flux times area, which we have. And here it is, 0.01 mole per second. Another interesting one will be, okay, if we have both of them, what do we want? No, where? Let me structure the question. So we have now moles per second. The idea will be how many times requires you to get 1 mole of oxygen transfer. And time will be calculated as follows. You will need to get the total amount of material, which is 1 mole of oxygen, and divide it by the rate, which is 0.013 mole per second, and this will give you the solution of seconds. And this is how we solve unimolecular diffusion cases.